Okay, we're ready to move on to the last part of this question. Here's our results from the 120 student school. So there was a 0.1244 chance that they were over 90 and same that they were under 86, so about 12, about 12.5% that were on each line. And if we wanted a 90% interval where 90% of the school of this size should land, they land between 85.15, so that's almost 3 points under the average, and they go up to 90.85, so that's almost 3 points over the average. Okay, so what if there's 1,000 students in this school? Well, that computation is going to be pretty much exactly the same as what we just did up here, except this denominator changes in our standard deviation. So the mean that we expect is still 88. The average student is 88, so the average school should be 88. But the variance is going to be different. The standard deviation is different. This 120 changes to 1,000. So what is our standard deviation going to be now? Our standard deviation now is square root of 19 squared. So 19 was the standard deviation for a single student, but now we're dividing by 1,000. So I'm just flipping over to my calculator, 19 squared divided by 1,000, take the square root. I get 0.6008. 0.6008. Okay. So we just need to change that one number in Minitab and redo the stuff that we already did. Okay, so let me bring up Minitab here. Probability distribution plot, view probability. Let's put in our new standard deviation, 0.6008. 0.6008. Okay. So first we'll do the probability that we get over 90. Okay, so I switch back to X value. I know my cutoff line is 90, a score of 90, and right tail, because I want to know the probability that our school averages over 90. We hit OK. And I get a pretty tiny number. So this is 0.000436. A probability that we get over 90 is 0.000436. And remember, that's the same as the probability for getting under 86 because this bell is symmetric around 88. The chances of getting 2 points over or better, that's the same as the chance of getting 2 points under or worse. It's just the tail on the right or the tail on the left, the same distance from the center. That is a lot lower than it was for the school with 120 students. Now, these are the same students. They have the same mean, 88, the same standard deviation of 19. The only difference is that we have more students now. When you take more students, it's sort of less likely that you have a pile that are at the high end or a pile are at the low end. Basically, like the more times you repeat your experiment, the standard deviation tightens up and you expect to be closer to the mean. So the chances of being 2 whole points above the mean is a lot lower than it was before. Everybody's going to be sort of closer to the average when you have 1,000 students instead of just 120. And let's look at the interval to see how much that tightens up. So let's find our 90% interval. This time we know the probability. This is all set up. The numbers are in there from before. We want a range that has 90% chance that we're going to land in. That leaves 10% chance that we're in the tails, split evenly among the two tails. So we do both tails, 10% for the two tails, hit OK. So we have a 90% chance that our average is going to land basically between 87 and 89. So the 90% interval is from 87.01 up to 88.99. Okay, so I'm going to flip back over to Word here, just so I can look at my results. Okay, so just to sort of distinguish these two schools, let me sort of summarize what's happening on the high end. So for schools of size 120, or 120 students taking the test, there is a 5% chance. So there's a 90% chance that they are in the interval we found. So 5% chance that they're higher than the high end and a 5% chance that they're lower than the lower end. So like each tail has 5%. So there's a 5% chance the school on average gets a score over 90.85. For schools of size 1,000, there is a 5% chance they score over basically 88.99. 88.99. And remember, there was pretty much no chance they got over 90. So for schools of size 120, there was like a 12% chance they got over 90 and a 5% chance that they almost get 91. For the big schools, the really good schools, they just get like 89. And there was pretty much no chance. It was well under 1%. What was it, like 0.04% that they would score over 90. Okay, so the point of this is that in the real world, there are states that use standardized tests to try to identify high-performing schools and low-performing schools. They run the same tests on the students, and they look at the school average. Well, looking at these numbers we just had, all other things being equal, and only the size of the school being different, you have a much better chance of scoring really high if your school is small. Basically you just have to get lucky and have a few strong students and a few less weak students, and you get a score that's completely unattainable for the big school. So unsurprisingly, the states that do this, like if they give sort of special bonuses to the highest scoring schools, they're all small schools. And it's not because the small schools are better necessarily. I mean, they might be good, but they have an unfair advantage. They have the potential to achieve school scores that are basically impossible for the big schools with the exact same type of student. And it happens on the bottom end too. They might give penalties to the lowest performing schools, and those are also all very small schools, because the big schools, they just always end up in the middle. They have such a big sample, everything averages out, they end up close to average. And the small schools, it's much easier, like they have a bigger standard deviation. They can swing higher, they can swing low. So there's like schools in states like North Carolina that have long done this, where a school will be among the top 10, and then like 5 or 10 years later, when their student body has turned over, they're in the bottom 10, just because it's random and their small size means that they swing more. So it's completely ridiculous to do incentives based on like standardized testing to like sort of reward or penalize the extremes, because the big schools always end up in the middle. The small schools, sometimes they end up in the middle, but the outliers are always small schools. Okay, so that is it for my last central limit theorem example. We'll move on to a next chapter in the next class. And I've been having some questions about what I plan to do about quizzes, so I am going to assign some homework questions that I'll attach to the end of this Word document and post on my website. And I guess I probably won't end up quizzing these questions. I just want you to try them, compare your answers to the answers that I also attached to this document, and ask me questions over email or in office hours on Zoom if you have any. But starting next week, I'm going to have the regular homework questions plus maybe one question that will be like the quiz of the day question. I'm going to try putting that in a D2L quiz because I know how to make D2L quizzes. But if D2L keeps having server problems, I might just have to have you either email me the answers, or I might have to find some free online survey software or something where I can collect your answers that way. Hopefully D2L works. When I tried to log in yesterday, it was okay. So hopefully D2L works. All right, and so I'll have something else for you for Friday with a new chapter.